Hi, myself Sudhir, and my teammates are Shivaram Krishna and Nithivaran Reddy. We are third group, and the topic we are presenting is learning-based query optimizer using neural networks. I would like to start with the outline of this presentation. These are the topics we'll be going through, like from introduction, some related work, and how did we achieve our objectives, and then we'll conclude with the demo. So let me start with what is meant by query optimization. There are multiple stages through which a query process, and optimization is one of the stage. And it is one of the most challenging problems in database systems. It compares different query strategies and chooses the one with the least expected cost. Basically, it is nothing but a process of choosing the most efficient means of executing a SQL query. This optimization of a query is done by the optimizer, which is a very key part of the DBMS system. And this optimizer determines the most efficient way to access the data. So good optimizers can really speed up the execution by multiple folds. But however, there are still a lot of constraints with respect to query optimizers. They have become extremely complex components, which requires a great deal of hand tuning for specific workloads and specific data sets. This is the overview of a query processing. These are the stages involved in how a query is processed. As we can see, it starts with a query and goes through parser and translator to convert it into relational algebra expression. Here comes our optimizer, which plays a crucial role in generating a plan which is a very efficient one. This plan is executed to generate the final output. Therefore, it can be viewed as there can be many different ways to get an answer from a given query. The result would be same in all the scenarios, but DBMS strive to process the query in a most efficient way to produce an answer, and this is nothing but query optimization is all about. Our main goal is to improve the performance of the query optimizer by incorporating a neural networks model. To achieve this, we are developing a learning-based query optimizer that relies on neural networks, which generates a query execution plans and written an efficient and least cost query plan. We compare the latencies of the queries with the learned query optimizer and with the already existing open source optimizers like PostgreSQL. And we also evaluate the performance of this developed optimizer with another optimizer which is being developed using machine learning based multi-objective reoptimization technique. So these are the objectives which we are trying to achieve in this project. So let me introduce some related work in this area. Basically, traditional query optimizers rely on static strategies. They do not learn from previous experience. These systems just plan a query, execute the query plan, and they forget that they ever optimized this query. And because of this lack of feedback, which we can get it from the previous experiences, this query optimizer may select always the same bad plan repeatedly, which is never learning from its previous bad or good choices. So in this project, we are trying to develop a learning-based optimizer that leverages this information from previously processed queries, which aims to learn how to optimize the future ones more effectively. That is nothing but producing a better query plans and spending less time on optimization. With the recent advances in machine learning, it is shown that using existing deep reinforcement learning techniques can be leveraged to provide better query plans using less optimization time. This neural optimizer we build takes a query plan as an input and predicts the best expected runtime. This pair of plan and time is fed back again to the neural network model to increase the efficiency for future queries. There are many other approaches proposed in this area, like adaptive query processing and multi-objective reoptimization, which aims to generate better query plans. Rejoin is also one of the technique, which takes care of only join order selection, but not physical operator and index selection, which are achieved in this neural optimizer.
Thank you, Sudhir. Now we'll see the proposed work. Coming to the dataset and source, we assess our NEO model on PostgreSQL SQL database framework. It's done by using IMDb database. Firstly, we create PostgreSQL SQL database, example name IMDb load. At that point, totally we create 22 tables in the database, and we supplement information into them. Following is the database made. The following figure shows the database we created in pgadmin 4. Now we'll see the sample queries we taken for training and testing. For training, we have taken set of queries over the Internet Movie Database. It comprises of complex joins and predicates. The arrangements of queries are encoded utilizing row vectors. This is the encoding technique which we are using in our model. Also, Neo has access to a PostgreSQL optimizer through which we are generating our query execution plans for each query in the sample workload. Here, all the query execution plans are encoded using tree convolution technique. These query execution plans, along with their latencies, are added to Neo's experience, which are used as a starting point in the model training phase. And firstly, we encoded the queries, and after that we will encode query execution plans, and then we join both encoded queries and encoded query execution plans and use them as a preparation set to our Neo model. Once the model is trained, we test it using 22 external job queries. For testing, we are using totally 22 external job queries. And now we will see the feature engineering part. In this project, we have performed feature extraction and selection methods using Python libraries like Word2Vec. In this project, totally Neo contains two encodings. One is query level encoding, and the second one is query execution plan level encoding. In query level encoding, we encode information regarding the query, but is independent of the query plan. Whereas in query execution plan level encoding, we encode the query execution plan. Coming to query plan encoding, for example, take this SQL query. In this, totally 4 relations are involved, and we have some predicates like involved between A and C, and in between A and D, and in between C and B, like that. A totally query plan encoding contains two components. The first component encodes the query's join graph as an adjacency matrix. Here, if you see the join graph, the one in the first row, the third column, corresponds to the join predicate connecting A and C. Furthermore, since this matrix is symmetrical, we will only encode the upper triangular portion. By taking the upper triangular portion, we will get the query level vector as the following one. As I told before, the totally query plan encoding involves two components. The first part is adjacency matrix, and the second component of the query encoding is the column predicate vector. In this, we specify only the attributes which are involved in any query predicate but not in join predicates. Here, the one hot encoded vector with the positions for attribute A.2 and B.1 set to 1, since both attributes are used as part of predicate. And make sure that join predicates are not considered here. And for one of the queries we used in our database, that is tenya.sql. For this query, we have generated the encoded vector. The following figure shows the encoded vector for that query. And now we'll see the query execution plan level encoding. And we'll take the example sample query in which 4 relations are involved. For every query plan, we generate the execution plan. It is done by using explain command. Firstly, we generated the execution plan of each query in JSON format. It is done by using command explain of format JSON. And then we transform the JSON structure into tree structure as follows. And here the query plan encoding preserves the inherent tree structure of execution plans. And we have number of nodes in a tree. Each node in a tree indicates the predicate vector as shown in the figure. And here, as I told before, that each node is a vector. Each node has a vector. Each node is a vector. So each vector size is mod j plus 2 mod r, where mod j is the number of join types and mod r is the number of relations involved in that query. And then associated scan type like table scan, index scan, and extra. For internal nodes, these entries are the union of the corresponding children nodes. Suppose, for example, if you observe this figure, here we have two leaf nodes A and D, for which the vectors are here table A has involved, so we'll place 1 under this. And if you consider the D node, for this the vector, we put 1 for D. And for the internal node merge join, here the merge join is happen. For this we'll put 1 for that. And as I told before, for the internal nodes we need to take the union of the child nodes. So we'll put 1 for A and D, and the process is continued for all the nodes. Now we'll see the row vector featureization. As I said before, we are using row vectors for training our neo volume model. To generate row vectors, we are using word-to-vec algorithm. Word-to-vec algorithm is a natural language processing technique which transforms natural language words, that is example English words, into vectors. It works on the distance based. While these vectors are meaningless on their own, the distance between them have semantic meaning. For example, the distance between milk and curd will be same, whereas the distance between apple and car will be large. And as I said before, in Neo we treat each row of each table in a database as a sentence, and we treat each column value of a table row as a word. Thus, values that frequently co-occur in rows are mapped to similar vectors. We call these vectors row vectors. A Neo's value network can take these row vectors as inputs and use them to identify correlations within the data and predicates with syntactically distinct but semantically similar values. For example, both action and adventure frequently co-occur with superhero. For our IMDb movie dataset, we train the word-to-vec model with the IMDb database. For example, if a query or the IMDb movie dataset or job dataset looks for all actors in movies tagged with Marvel Comics, the query will return many actors who play superheroes. Similarly, if a query looks for all actors in movies tagged with Avengers, the query will also return many actors who play superheroes. However, a query for all actors in movies tagged with romance is unlikely to return many superhero actors. It is achieved using word to vector. And as I told before, totally we have two encodings. One is for query encoding and the second is for query execution plan encoding. For query execution plan encoding, we are using tree convolution technique. As neural network models like CNNs take input tensors with a fixed structure, such as vector or an image. For NEO, the features embedded in each execution plan are structured as nodes in a tree. Tree convolution slides a set of shade filters for each part of the plan tree. Intuitively, these filters can capture a wide variety of local parent-children relations. For example, filters can look for hash joins on top of merge joins or a join of two relations when a particular predicate is present. Since the output of tree convolution is another tree, multiple layers of tree convolution filters can be stacked. The second layer of filters will be applied to the output of the first. Now we will present two concrete examples that show how the first layer of tree convolution can detect interesting patterns in query execution plans. Here we have two examples, example 1 and example 2. In example 1 of figure 7a, we show is 1a, b, c and d. In figure 7a, we show two execution plans that differ only in the topmost join operator. That is a merge join and a hash join. As depicted in top portion of figure 7b, the join type hash or merge is encoded in the first two entries of the feature vector in each node. A tree convolution filter, if you observe top figure C, a tree convolution filter comprised of three weight vectors with 1, -1 in the first two positions and the zeros for the rest will serve as a detector for query plans with two sequential merge joins. This can be seen in figure D top. The right node of a plan with two sequential merge joins receives an output of 2 from this filter, whereas the root node of the plan with a hash join on top of merge join receives an output of 0. Subsequent tree convolution layers can use their information to form more complex detectors, like to detect three merge joins in a row, or a mixture of merge joins and hash joins. And in example 2, figure 7, suppose tables A and B are sorted on the same key and are thus ideally joined together with a merge join, but C is not sorted. The filter shown in figure 7C bottom serves as a detector for query plans that join A and B with a merge join behavior that is likely desirable. The top weights recognize the merge join, the right weights recognize table B over all other tables. The result of this convolution is shown over here. Next part will be continued by Nitivan.
Thank you, Shiva. So right now I'm going to talk about value network. And value network is a core part of our optimizer. It is the actual neural network which is trying to predict the best possible query latency for the execution plan. So as you can see, this is a value network architecture, and this architecture is designed to create an inductive bias suitable for query optimization. So the structure of the neural network itself is designed to reflect an intuitive understanding of what causes the query plans to be fast or slow. So as I've earlier said, in general, patterns are recognized by humans, like a merge join on top of an hash join with a shared join key is likely inducing a redundant sort or a hash join, and a series of merge joins that do not require resorting is likely to perform well. So our insight is that the value network learns all these patterns itself when the data is given to it by taking advantage of the technique called tree convolution, and I'm going to explain the how the tree convolution is done in the next slide.
So the tree convolution works, the value network works in the following way. So when the partial query is fed into the value network, it first gets the query encoding and the plan encoding of the partial execution plan. So these two are combined using spatial replication technique, where when the trees are of dynamic size, then we combine it with using this technique, and then these trees are sent to a three convolution layers over where the trees are mapped into a dynamic pool operation, which then flattens the tree structure into a single vector, and this single vector goes through other several layers, and finally it becomes one value, and that value is the model's prediction time. So the value network now just gives us the execution time, which is the quality of the plan, but not the execution plan. So for searching the final execution plan, we combine our value network with a search technique, resulting in a value iteration technique. Now, using our value network, when an incoming query is given to Neo, then it performs a search over the plan space for the optimal plan. This search is similar to the way the traditional database optimizers do the search for the plan, but the only change is that now our value network acts as a cost model which fine-tunes the search and gives us the optimal plan, which is then given to the executor for execution. So now let's talk about the results. We have generated all the encodings of queries of the job dataset along with the query execution plan encodings, and we could get an output with Neo, but when compared it with the traditional Postgres query optimizer, we could only reduce the latency time by 10%, and here's the graph. Now this result shows us the learning curve. This explains that Neo is learning from the past query plans, and the latency of the query execution is getting reduced compared to the traditional Postgres optimizer as the iterations are getting increased. And you can also see it from the graph. So from the results you can see that Neo iteratively improves its performance through reinforcement learning and search strategy. But because of the configurational constraints, we could only limit our training iterations to 25. So we assume that increasing the training iterations will lead to better learning and provide more optimized results. Right now, Neo is also schema specific and it is generating good results when trained on IMDb dataset. But in future, we think that a more generic model can be developed using Neo as a base so that we can get good results on any dataset.
Hi all, I'm Sivaramakrishna Ganta and my team members are Nithivaran Reddy and Sudhir. We belong to group number 3. Now I will show our project live demo. Uh, we assessed our NEO model on PostgreSQL framework. For that, firstly we created IMDb load database in PostgreSQL. At that point, totally we created 22 tables in IMDb load database and inserted data into the tables. Totally the size of the database is around 6 GB. And now I will show the important part of our project. As I told, that Neo involves two encodings. One is query level encoding, and the second is query execution plan level encoding. Now I will show how we generated encodings. This figure shows the train go-to-back model. Now we will generate features. And following are the features. We generated the features in files, and the features are stored in pickle files. The following are the feature files. Now I will show one SQL file for you. Hi all, I'm Sivaramakrishna Ganta and my team members are Nithivaran Reddy and Sudhir. We belong to group number 3. Now I will show our project live demo. We assessed our NEO model on PostgreSQL framework. For that, firstly we created IMDb load database in PostgreSQL. At that point, totally we created 22 tables in IMDb load database and inserted data into the tables. Totally the size of the database is around 6 GB. And now I will show the important part of our project. As I told, that NEO involves two encodings. One is query level encoding, and the second is query execution plan level encoding. Now I will show how we generated encodings. This figure shows the train go-to-back model. Now we will generate features. And following are the features. We generated the features in files, and the features are stored in pickle files. The following are the feature files. Now I will show one SQL file for you.